Hello, everyone, and thanks so much for joining us for another topic in chemistry as we continue to understand more about how we put atoms and compounds and solutions and different parts of a chemical change into the format of an equation. So, the focus for today, go ahead and set up your focus note page. Our topic is chemical equations, and our essential question is how do I use symbols to represent a chemical change? So, eventually, we're going to be writing something that looks like this so that these are not just random letters and symbols and words or in little pieces and numbers, but something that means something to you as a chemist. This is one of those kind of foundation skills we need to keep moving forward. Go ahead and fill in whatever date you're taking these notes, and let's go ahead and get started. All right, so our focus today is a chemical reaction. Quick reminder, you just because we haven't taken notes for a while, remember you only need to write down the stuff in red. The other kinds of colors are things that I just want to talk about, but the notes are the stuff in red. All right, so just to review, a chemical change, remember, is a change where the identity changes. And that's the same as a chemical reaction. We're going to start using this term now more than this term. This was kind of an introductory term, physical and chemical changes, like in our first unit, but now we're going to start talking about chemical reactions. So, a quick reminder, so a chemical reaction is when the identity of an object changes. Those atoms that you had present have changed and done something different, so now you have a new identity. When you have a chemical reaction, there's three things that the atoms involved will do. They can separate, so whatever bonds were present can pull apart and unattach, or you can make new bonds. So you had separate things at the beginning, and now they combined, they came together, they made new connections, new bonds. Or they can rearrange. You had a couple things to start with, and now you have a couple different things to end with. So that idea of separating, combining, or rearranging, that's how we're going to describe chemical reactions right now. So if atoms have separated, we know we have a new identity. If atoms have combined compared to the beginning and the end, we know there's a new identity. If the atoms have rearranged their bonds, we know there's a new identity. So we can use those kinds of ideas to know, this is a chemical reaction. Something new has been made. When we write chemical equations, think of that kind of like the words of chemistry. So, just like in the English language, or many other languages, of course, before you learn how to read or to write sentences, you learn the individual letters. So, think about, when you were young, you learned the alphabet, and then you put it together into simple letters or simple words, and then you learned how to read simple words and write simple things, and then you just got more and more complicated. Well, in chemistry, before you can learn about writing reactions and chemical equations and writing formulas, you need to learn about elements. But hey, we already did that. We know some things about elements and element symbols and writing formulas. We know a little bit about that. But why don't we do a quick little review? So we know about elements. Elements come together to make formulas to make stable compounds. And a formula really is a combination of letters and numbers that represent a stable compound. When we look at a formula, it tells us two things. It tells us what elements are there and how many, what is the number of each atom. So if you saw something like this a while ago, this would mean nothing to you. But now you have a little bit of understanding that this is a certain thing that we have three of. There's PO4s, and those mean something. N is nitrogen, H is hydrogen, P is phosphorus, O is oxygen. Those aren't random letters anymore because we have a little background in chemistry. And then the numbers tell us how many there are. We know that parentheses keep a group together and numbers outside multiply in. So there's three N's, 3 times 4 is 12 H's, 1 P because there's nothing next to it, and then 4 O's. So that is the purpose of a chemical formula, to tell us what elements are in this compound and how many do you need of each of them to make a stable and neutral compound. All right, but then here's the part we really need to review. How do we know what elements to use and how many of each? Like, how do we know there was 3 of this NH4 and why is it NH4 instead of NH2 or something like that? All right, so let's go back to your notes here. Let's review element formulas. Well, most of the time you just write their symbol off of the periodic table of the elements. But remember, we have these things called the 7 diatomic. Di means 2, atomic refers to atoms. These are those 7 elements that can never be by themselves. And These are the 7 diatomics: iodine, bromine, chlorine, fluorine, oxygen, nitrogen, hydrogen. When we write their symbols, we would never just write a capital I by itself. It would either be in a compound with something else, or we have to put I2, Br2, Cl2, those kinds of things. Here's a little trick to help you remember it. Brother, Cliff. A silly little sentence to help you remember the 7 diatomics. The brother is representing bromine, so Br, like brother, for bromine, and then H for hydrogen, O for oxygen, N for nitrogen, Cl for chlorine, I for iodine, F for fluorine. Brother, Br, Cliff. So just a silly thing to help us remember those 7 diatomics, because there's 111 elements that you just write their symbol like normal. But these 7 exceptions are things that can never exist by themselves. And so instead, we have to know this thing that their symbol would really be I2 instead of capital I, or Cl2 instead of just a capital C, small l. So that's just one of those little exceptions we have to be aware of as a chemist. Well, what if it's not an element? What if it's a compound formula? All right, well, the first thing, remember that you check. This is what we just did in our unit 2, but it's a good chance to review. The first part of the compound, check to see if it's a metal or a nonmetal. And remember, you've got that dividing line we drew on the periodic table that looks like stairs. The elements on the left of those stairs are always metals. The ones on the right are always nonmetals. So if it's a metal first, we look up their charges, their oxidation numbers, and then we do that chemistry math to make the total positive charge balance the total negative so that you get a stable neutral compound. So for example, if I was making a compound with calcium and phosphate, I would look up that, okay, calcium is a metal. It's on the left side of the periodic table. It has a positive 2 charge, and phosphate, that would come from the ion guide sheet, that is a negative 3 charge. These don't match each other right now. So I've got to do some chemistry math and find a number they both agree on so that the total plus equals the total minus. So I can do my multiples like in math, and I can say, 2 and 3 multiples could both turn into 6. So I could say if I have 3 times 2, that would be positive 6. And if I did 3 times 2, that would be negative 6. So if I have times 3 of this whole thing and times 2 of this whole thing, the positive and the negative will balance. That's the chemistry math. And then my answer would look like this: 3 particles of calcium and 2 particles of this whole group, which is why I put the parentheses around it. This was what we were learning in Unit 2. If you still have questions about it, I invite you to come to my office hours soon, or ask during Zoom, or send me a message, and we can make sure that this makes sense while we move forward. That's what we do if there's a metal first. However, if there's a non-metal first, you're going to just look at the prefixes. So before we do our break, so you're just going to look at the prefixes. So in the name of the chemical, the compound, like something like dinitrogen, trioxide. Nitrogen is a nonmetal. The prefix di means 2, and then tri means 3. Oxide means the element oxygen. So dinitrogen trioxide would be like N2O3 would be the formula. So compound formulas, check to see if metal or nonmetal. Metal balance charges, nonmetals look at prefixes. Okay, now you know what's next because you already saw it. We're gonna take our first little break. So you have a chance right now. You could pause the video, go do a little stretch, take a drink of water, but then also do your Costa questions. If you need a guide for Costa question center starters, remember you have that guide on Schoology. But do a level 1 question right now. Remember the purpose of level 1, it comes right from the notes. You've got these different keywords like list the 3 things that atoms do to make a chemical change. That was one of the first things in our notes, right? Let's see, describe the steps for writing a metal first compound, something like that. But you write your own Costa level question 1, pause the video, come back when you're ready. All right, let's continue on. So a chemical equation uses symbols to show before and after a chemical change. So what things did you start with? What happened? What things did you make at the end? That's the purpose of a chemical equation. It's like a shorthand sentence to describe what happened in the chemistry of a lab, or something happening in an experiment, or something happening in the world, or something you're trying to make happen. Wherever it happens, it shows the before and after. So the parts of a chemical equation, this is generally what a chemical equation looks like. Now, not every chemical starts with two, or equation starts with two things and makes one thing, but there are something that every equation parts will have. There will always be reactants. Whatever is on the left side of an arrow are your starting chemicals. There will always be some type of plus sign somewhere. There might be three of them, there might be some on the other side, but there's always some type of plus to show that these two things are separated. They are not bonded right now. The plus is kind of like the word and. So like zinc and iodine. This is that reminder that iodine is diatomic. That's why it's not just capital I, but zinc is not diatomic. So it can just be ZN. Okay, then you're always going to have some type of product. So again, this one happens to be one product, but there could be 16 different products depending on your chemical reaction that is happening. These are your ending chemicals. So what did you start with? What did you end with? Things that are not bonded are separated by plus signs, and then you will always have some type of arrow. The arrow separates the reactants from the products. An arrow means something happened. There was some type of chemical reaction. We don't know if it was really simple like this one, or the atoms separated, or the atoms rearranged. Doesn't matter what type of reaction, but any type of chemical reaction would have an arrow somewhere. So if I'm asking you to write a chemical equation, you always know there's going to be an arrow. You always know there's some type of starting chemical and some type of ending chemical. So this would read kind of like zinc and iodine make a reaction to produce zinc iodide. That would be the idea. So in shorthand notation, you're showing the chemistry that happened. The atoms combine to make a new substance, a new identity. It turns out, though, that sometimes we're going to have special arrows to tell you a little bit more information about the reaction. So you could put the word heat or a triangle on top of an arrow if the reaction will only happen when you add heat. So if you have to use a Bunsen burner or put it on a hot plate or put it in a microwave or put it over a fire, that means that you need to put the word heat or that triangle on the top of the arrow. Another thing you can do is you could put a chemical formula on top of the arrow to tell us that that reaction will only happen if you have a catalyst. That formula on the arrow is your catalyst. Now, catalyst might be a word that you remember from biology, or maybe you remember the word enzyme from biology. So pause right now. Can you think what that means? Do you remember? Oh, your bio teacher would be so impressed. Think, think, think. All right. A catalyst is a substance that makes a reaction speed up or go faster. But it's not really a reactant and it's not really a product. So that's why we don't put it on the left side of the arrow or the right side of the arrow. We put it on top of the arrow. So enzymes are catalysts that are inside living cells. So that's why I said you might have talked about it in biology, but it's okay if you don't remember that word, no problem. A catalyst is what we call it in chemistry for something you add to a reaction to make it speed up. Okay, so those are a couple special other things you might put in a chemical equation. You have your reactants, you have your products, you have your arrow, but maybe you had to heat it up. So you put an arrow on, triangle on top of the arrow. Or you had to add a catalyst. So you put a chemical formula on top of the arrow. So that's a couple little special details. All right, go and take your second brain break. Again, if you need to pause the video and go stretch or go use the restroom or take a drink of water or, I don't know, have a dance break. But then at some point, write your level 2 kind of question. Level 2 questions, the thing about them is there's a hint in the notes, but your brain has to finish it. So a little bit higher level. Here are some Costa level 2 questions if you need. Otherwise, you've got that guide on Schoology with a whole bunch of really good sentence starters. That would be a great way to write your level 2 question. All right. Oh, I sketch a generic version of a chemical reaction. That would be kind of cool, or a chemical equation. You come up with your own. Okay, pause the video, come back when you're ready. All right. One more little detail that we have to learn about a chemical reaction is that we will use subscripts. Sub means like underneath, like a submarine is below water. So a subscript are those little numbers you put or letters you put next to something kind of down below. And we're going to show the states of matter. So we're getting more details. So instead of just the chemical formula, we're also going to think about, is it a solid, a liquid, a gas, or a solution? So here's do some examples. If you had solid carbon, you would say, oh, well, carbon is an element. It's on the periodic table. The symbol is capital C. For solid, you're going to put a little parentheses and an S inside it. Without the parentheses, it might look like it was part of the chemical formula, and that would be confusing. So this means solid carbon. You would put that in a chemical equation. If you had liquids, you would do that same kind of thing, but instead of an S for solid, what do you think you're going to use for liquid? Guess? Yeah, you're going to use an L. Okay, so water might be one of those formulas you just know. It's the common name for dihydrogen monoxide. So 2 hydrogens, 1 oxygen, H2O, and then you put the little parentheses and the L. This is a subscript. When it's down below and little like this, that's what we mean by subscript. So liquid, water. All right, what if we had a gas? All right, what do you think we're going to look like there? Predict, you got it? Gas, yeah. And then hydrogen. Okay, well, hydrogen is an element, and we look on the periodic table, and it's capital H. Oh, but remember those diatomics? Do you remember what the trick was? Quick, pause the video if you need to. Look back in your notes. What's the trick for remembering the diatomics? Yeah, Brother Honcliffe. So Brother Honcliffe, that H is for hydrogen. So we don't just put H, we have to put H2, and then we put the little g in the parentheses down below to make it a subscript. That tells us that this is gas hydrogen. Now, those are the 3 states of matter that we generally think about in science. However, another special thing is, well, what if it's a solution? Now, here's the tricky thing. A solution could be any of these states of matter. Usually we think of solutions as liquidy because they're mixed with water. So what we're going to use is, if it is a solution, something that is mixed with water, we can't call it liquid because liquid means that's only that substance. There's nothing mixed together. But we can't use S for solution because we already have S for solid. So it turns out we use something called AQ. AQ stands for aqueous, like the word aqua. Maybe you've heard of that. So AQ means that you have this chemical mixed with water. It's a solution. So if you're dealing with a solution, which we often do in chemical reactions, you put that AQ to show this is not pure sodium chloride. It's sodium chloride mixed with water to create a homogeneous mixture. Maybe that's another word that you remember. So states of matter subscripts is the last little detail that you need to learn in addition to writing formulas, writing compounds, remembering diatomics. So yeah, there's a lot to practice right now. So let's do one together, all right? Here would be the chemical reaction. Hydrogen peroxide solution breaks down to form water vapor and oxygen gas. This reaction is sped up by a potassium iodide catalyst. Whew, oh my gosh, that's a lot of information. We got to take this in little pieces. Here, look at this. It tells you there's a reaction. So what do you think you might start with? What did I say every chemical equation has? Do you remember? An arrow. So start with an arrow, because then at least you've got something written down on your page. But then now we have to figure out, what did I start with? That goes on the left. What did I make? That goes on the right. And we have to check to see if there's any special arrows. Let's just take it in little steps and start at the beginning. Hydrogen peroxide solution. All right, hydrogen is an element. It's bonding to something, so we do not worry about it being diatomic because it's in a compound. So hydrogen has a +1 charge. Peroxide is on your ion guide sheet. The symbol is O2, and it has a -2 charge. So we got to do some chemistry math. We take this times 2 because I have to give away 2 electrons to make that -2. So 2 H's, and then I don't change this formula because I didn't change anything about it. So O2, hydrogen peroxide. It says it's a solution. We learned that means the state of matter is AQ for mixed with water. So AQ is solution for aqueous. Remember, that's that new little vocab thing we just learned. So the first thing I'm going to write down is hydrogen peroxide, aqueous in my formula, H2O2AQ. That's what I'm starting with, and it says it's breaking apart. So that means that nothing else is being added to it. There's no words that say added to or and or mixed with or anything. It's just that. So that's why it's the only thing on the left side of my arrow. It breaks down to form. That is your arrow, breaking down to make something new. Water vapor. Well, again, water is maybe one you already know, or I'm going to give it to you. It's H2O. And then vapor means the same as gas. Oh, there's another little vocab word we have to be familiar with. So water is H2O. vapor means the same as gas. So one of the things that goes on the other side of the arrow is H2O with that little G, water vapor. But then look at that little word, and. Remember what we use for and? Can you remember? Quick, before I say it? A plus sign, yep. And then oxygen gas. All right, oxygen is an element. It's not combining with anything else, but remember, diatomic oxygen, Brother Honcliffe, right? So oxygen is capital O, but because it's diatomic, we put O2. This one makes it more obvious, gas, so we put the little G next to it. So O2 gas. Whew, okay, that's a lot of stuff, but we're not quite done. It says that this reaction is sped up by a potassium iodide catalyst. Remember that vocab word catalyst? Catalysts go on top of the arrow, but we don't write out the name potassium iodide. We have to figure out the symbol. So let's review. This is a compound. Potassium is a metal. Because potassium is a metal, that means we're dealing with balancing charges. So potassium is capital K, has a +1 charge. Iodide is really just the element iodine, -1. And again, it doesn't matter that iodine is a diatomic element because it's not an element right now, it's a compound. So +1 and -1, perfect match, Ki. Catalyst means you put the formula on the arrow, Ki. So this big thing that we did represents this 2 sentences. So hydrogen peroxide solution breaks down to form water vapor and oxygen gas sped up by a potassium iodide catalyst. All right, so this is what you already did. Let me ask this follow-up question. Did the atoms separate, combine, or rearrange? We have one thing, and now we have 2 things. So what happened? Separate, combine, or rearrange? Which is it? Yeah, they separated. These bonds broke, and they made 2 new things. The atoms separated. And guess what? You've actually seen this reaction. Remember the demos where I did the signs of a chemical change? This demo with that big foaming thing? That's the chemical equation to represent this reaction. The hydrogen peroxide broke down when I added that catalyst and I made gas. How do I know there was gas? Look at all these bubbles, right? So this was a fun reaction that we already saw, but now you know the chemistry that you would use to represent that really fun chemical change. Okay, now here's the tricky part. There are so many details and so many little things to think about, but I promise it gets easier with practice. So here's some things to help you. You're always going to have at least one starting chemical, you'll always have an arrow, and always at least one ending chemical. So I recommend you start by just drawing in an arrow, because then at least you've started. Then take the description like we did in those underlines, 1 or 2 words at a time. Put the symbol on the left or the right of the arrow until you've gone through the whole description. That's kind of a good place to start. And then there's just lots of little details that you've got to practice. Check for any special arrows. So if it says that the reaction was heated up, or if it says there's a catalyst, don't forget about those special arrow possibly. But sometimes there won't be anything. It'll just be a normal arrow. All right. And then you got to remember those diatomics if you're writing elements, and you got to remember our rules for writing formulas. Metals and nonmetals, you balance charges. Nonmetals, you look at prefixes. Lots and lots of details. I know that. But the good news is it will get easier with practice. So that means we should probably get to practicing here pretty soon. Before that, though, quick, do your last brain break. Our notes are done. Do a level 3 kind of question. You could do some type of defend the importance of writing chemical equations. Maybe there was some teacher that's like, oh, we don't need to do chemical equations in chemistry. They don't matter. How would you defend that? Or you could do any other type of level 3 question. Look at your Costa question guide if you need some ideas for sentence starters. Go ahead and pause the video, write your level 3 question, come back when you're ready. That brings us to the end of the first day of this new unit. Here is your to-do list. Finish your Costa questions if you did them, and now go back and write your summary. In general, remember the EQ was, how do I use symbols to represent a chemical change? Answer that question. Then I do have a practice assignment I want you to start. We will have time in our next Zoom to go over it, to ask questions, to do some breakout room practice and compare answers and get help. But of course, you can always use my office hours if you have questions, if you want to get a little jump start on it. But it is important you at least open it and try it so you're ready for our next Zoom to do some work and some trying and some practice with it. All right, so that means I will see you at our next Zoom session. Thank you so much for your attention today as we understand more about chemistry. See you next time. Bye.